All right, so guys, section 10.8. As we can see here, section 10.8, graphs of polar equations. That's the overall section 10.8 title. We break this down into Rose curves and then what we call limacons later on. Okay, so again, the Rose curves, what we're going to get into today. The limason, what we're going to get into. That'll take a couple of days to get through the limason because there are 4 different types of limason. Rose curves, there's we practically say an infinite number of types, but it's just that if you have 3 petals versus 4 petals versus 5 petals and things like that. The other thing that I want to point out, just so we're aware, it would probably be more appropriately named a flower curve. Again, they don't really look like roses necessarily, but they do somewhat resemble the shape of a flower. So, again, they've always been referred to as roses. I'm no botanist, but I don't think it looks much like a rose. It does resemble that flower shape somewhat. But again, this is the way that we're going to be graphing. So again, if you think about like in a rectangular coordinate plane, we've got all different types of your quadratics, with the parabolas, and your cubics and your square root functions and all of those parent functions that we learned back in August, or reminded you of back in August. And then that progressed into all the trig stuff. We even had the conics. Again, there's a lot of different types of graphs that we could put in a rectangular system. Well, we also have some types of graphs that we can and will put into the polar system. So again, that's what we're getting ourselves into starting today with these Rose curves. So the goals that we have in mind: students to be able to recognize special polar graphs. Number 2, students to be able to use symmetry, zeros, and maximum R values to sketch Rose curves. All right, somewhat I feel like a broken record that kind of present this the exact same way, regardless of the lesson, but we're at this level in mathematics that whenever you learn something new, it might feel a little uncomfortable until you have a chance to practice a few, I was going to jokingly say a few hundred times, but it'll really only take a couple of times, and you're going to start to see that it's all a pattern. Oh, if it's a Rose curve with sine, I do this. If it's a Rose curve with cosine, I do that. The good news is that regardless of whatever the numbers are that are also associated with the equation, you're going to find that, they obviously are going to matter. They're going to alter the graph, but what I'm trying to say is that it's pattern-based and that we're going to do the same thing every single time you have a sine. We're going to do the same thing every single time that you have a cosine. So it's really just a matter of getting the pattern down. And one of the first obstacles that we have is to understand the terminology because it's new. Again, we've never done this before. So again, in much of pre-calculus, I've been able to, kind of have the ability to say, all right, well, remember back in Algebra 2 when we did this. We're just going to go deeper or further with that now. We don't really have that luxury here now that we're in the polar system because this is, like I said, again, it's all brand new. So I'm just like I had attempted to set it up when we started section 10.7 a few days back. I'm being very intentional here when I'm not saying that, all right, guys, this is really hard. I'm not saying that. You haven't heard me say that, nor will you hear me say it that way or present it that way. This is very manageable, very doable. It's just that we have to understand the terminology first, and we have to see the pattern second. Once we see that, again, I'm expecting a lot of success out of this, and you should be too. All right? So as a reminder, know that we kind of touched on this actually within 10.7. We were graphing or plotting those polar coordinates. We said that if you were thinking that you were done with the unit circle, not really. Again, not only for specifically here with the polar coordinates, but also if we were thinking about, well, we do have a final coming up, and a major aspect of second semester pre-calculus has been knowledge of the unit circle. So again, if you're bored in these next couple of weeks and you just can't find anything to do, fill out a unit circle or study the unit circle or something like that. But again, we want to get back to where that's a strength and we know exactly what we're doing there. So I just wanted you to have this in your notes. If you need to refer back, that's where it is. But at one point, and it really wasn't that long ago, at one point, 5-6 weeks ago, you probably knew this thing inside and out. Hopefully, we still know this thing really, really well. Maybe we need to study it a little bit more, like I said, but it's going to come back to you much quicker than you may initially think. All right, so symmetry. not a new concept in mathematics. Can somebody explain to me what symmetry is or what it means in reference to a graph? Ben, what do you think? Yep, so it looks the same in reference to a line, I think, if I heard Ben correctly. Maybe we could add on to that a little bit. Absolutely correct with everything that was said, but what do we think? Does anybody have anything to add on to that? Laura, yeah, I often think of that in terms of folding as well. So again, if we have a line of symmetry, that line that Ben referenced, let's just think of a parabola. How about that? Again, think of your parent function for the parabola, your quadratic parent function, f of x equals x squared. All right, we can all envision that vertex at the origin opens upward. Do we agree that that y-axis splits the parabola exactly in half vertically? Right? It does, yes? Okay, so if that's the case, if it splits exactly in half vertically, okay. You bet. Thank you.
They gave me a broken loaner.
That was very nice.
So I had to go back there and get a second. I want to replace the computer altogether because it replaced the case on it. This used to not be.
All right, so guys, so back to this. Like we were saying, that line of symmetry again for a parabola. We're thinking about that y-axis, again, that vertical y-axis. If you were to quite literally take that parabola and fold it over the y-axis, the left side of the parabola is going to map perfectly or match perfectly to the right side of the parabola. That's symmetry. That's what we're talking about. Again, in various previous classes, you've really focused on where are those lines of symmetry and things like that. We're going to also focus on symmetry here. It's really a shortcut, frankly. It's going to allow us to see some patterns that are emerging, and we just have to, keep in mind that we're going to have symmetry. Now, where things might, again, this is all a comfort level type statement. If we were talking about rectangular, absolutely we would feel comfortable talking about x-axis, y-axis symmetry. Since we're in the polar system, remember that there is no x-axis, there is no y-axis. We have a polar axis, so you'll notice that anytime we have a cosine function, it's a Rose curve with a cosine function, you're going to be symmetric with respect to the polar axis. Okay, so if you're thinking, oh, that's horizontal, so it's like what we would refer to as x-axis, you're absolutely right. But again, it's polar axis symmetry. However, it maybe gets a little bit strange is if we have a sine curve. That's where we would typically think about vertical, but we don't have a y-axis. We say that we're going to have symmetric to the line theta equals pi over 2. Now, if you think about it, is that the vertical line? It is. So we're talking about the same thing, we just have different names for them because we're in a different system. Okay? Any questions so far about the symmetry? I think it'll click a little bit more when we actually see some graphs and things like that. Okay? So here are the two equations that kind of our basic kind of template equations here for Rose curves. We, as you can see, are looking at this that we've got r is equal to a cosine n theta. We have r equals a sine n theta. So I'm sure that we're seeing very quickly that the only difference between the two is that one is cosine, the other is sine. Okay, everything else matches perfectly, identical, the exact same. So what we really care about here is that, again, if you think back to like an ellipse, we needed to know HK, A, B, and C. Okay? If we have a Rose curve, we need to know A, we need to know N. Those two pieces are going to tell us the story. And we need to know if it's sine or cosine. Don't get me wrong on that. So again, identifying sine or cosine, identifying A, identifying N. So oftentimes where some students go is, well, what if we have a tangent? Well, then it's not a Rose curve. Okay? Like I said, these are literally our only two options for equations that lead to the Rose curve that we're talking about today. All right? So a typical Rose curve, I was a little ambitious when I thought I had it all figured out. I was graphing this. It just ends up looking like a mess now. So I'm going to try to highlight this first one in red. So this is our first Rose curve that we're going to look at or talk about. All right, so there's Rose curve. I'm actually just going to get rid of these others, just so we can see. So typically how we would sketch this up or draw this up is to look something kind of like that. Okay? To where I put extra lines in there, we know hopefully that this, hopefully, what do we call that point right there? Please don't say origin. What do we call that? That's the pole. What do I call this axis right there? That is the polar axis. So like I said, the black lines that I drew in there, that was just more to keep things straight, we could see. But what are you going to tell me? Is that symmetric to the polar axis, or is that symmetric to theta equals pi over 2? It's vertical to theta equals pi over 2. Okay, we can see the symmetry. Again, quite literally, we have a line drawn in, and if I fold it over that vertical line, points are going to map from left side to right side. Okay, so what this really is going to boil down to is, like I said, recognizing sine versus cosine, which, if this one is symmetric with respect to theta equals pi over 2, what do we have? Is that a sine or is that a cosine that we were just looking at? If all sines are symmetric to theta equals pi over 2 and all cosines are symmetric to the polar axis, what are we going to say this sketch is over here? This is a sine curve. Okay? Again, sine automatically symmetric to theta equals pi over 2. So we can just look at a picture and we could tell, oh yeah, that has vertical symmetry. It's a sine curve. If we didn't know the equation, we could build it on our own. The other two pieces, of course, that we need are A and N, whether it's a sine or a cosine. We need to know A, we need to know N. So A, that's going to tell us the length of the pedal, or what we call the maximum R value. All right, so go with me on this little journey, if you would. What does R represent? Just in general, what is R? Distance. The distance from the pole. So if I have, say, this point right here, could I figure out R is just whatever this distance is from the pole to that green circle that I just plotted there? That would be R, wouldn't it? Well, if I'm going along this rose curve, is R changing as I'm getting closer to the pole? Or is R changing as I'm getting further away from the pole? Or wherever I'm going? Again, yeah, R is going to be a constantly change. We have like an infinite number of R values, but we're going to have an R value specifically right there, and right there. That is the absolute furthest away that we could be from the pole. Do you agree? The way that that's found or calculated is that I started here on the pole, and I'm going further away. Then there hits a point to where now I'm getting closer. Again, we're looking for that point to where it changes, right? And again, I think that it's just easier to think through this logically, that there comes a turning point, if you will, that is the maximum distance away from the pole. So if that's what we have, we call it the maximum R value. That's the biggest length on these pedals. Okay, by the way, we didn't really define them yet, but do we see that these are 3 pedals? That's what we're going to refer to. So A is going to tell you the length of those pedals, or our maximum R value. So in this one, I'm just going to ballpark it here. Let's say that distance is 5. That distance is 5. That means that, A must be 5 because my max R value is equal to 5. Does that make sense how we got there? Now, is it going to be the same for all of these? Absolutely. Again, wouldn't make much sense to say we have a max R value of 5, and then I have a max R value of 7, I have a max R value of 3. Like, no, there's one maximum. Maximum means the largest. Right? It's going to be consistent all the way throughout. Okay? So A is going to tell you the length of that pedal, what we call the maximum R value. N is going to help us to determine the number of pedals. Okay. If you have the graph, it's easy. You just count. Typically, you're not going to have the graph unless you're trying to build the equation. You're not going to have both, I guess is what I'm trying to say. What we're going to be doing a lot of is, here's the equation, let's draw the picture. We're also going to be going, here's the picture, let's work backwards and write the equation. Just like we did with conics, just like we've done with all the other different types of functions. But N is going to tell us the number of pedals. Now, if it's an odd number for N, super easy, because it's like that one-to-one direct pattern, okay? If N is equal to an odd number, that's exactly how many pedals you have. So if N is 7, you have 7 pedals. If N is 5, you have 5 pedals. If you have 3 pedals, what must N be? N's going to be 3, because, again, that's an odd number. But if you have an even number for N, you have to double it to determine the number of pedals. So if N equals 2, you actually have 4 pedals. If n is equal to 16 times 2, you have 32 pedals. Not that we'd ever